So today is all about test. That will be a week from today. Now, I will be, since I scheduled a test on that day, I'll actually be traveling. Professionally, not Mardi Gras related. So one of my graduates retrieve a test, and in case of that she can handle, she won't be able to reach me in case it comes up. But I can try to make sure that a practice test that it'll be fairly straightforward as to at least what you need to do, what each question is asking for, and it's a matter of carrying it out. So what I'm going to do first is talk about the different types of problems that will show up in the test. So one problem of each type. And then during the rest of the time, we can discuss the practice test, any questions you have on that, and its solution. Okay. All right, so I'll give you a general approach to each one. Now I want to emphasize these types of problems will appear on the test in whatever order. It will not be the same as a practice test. It's up to you to recognize which type of problem it is and then how to proceed accordingly. Okay, so first, you know what? This marker is awful. Oh, just missed. Okay. Okay, so first, much better. Linear equations. So we have the equation of either is y prime plus a function of only t times to some q of t. So the key here to recognize a linear equation as something as opposed to something that's not linear is how y is involved. That you have a y prime and then just a plain old y by itself. There's no other function of y that's allowed. If you have a y squared or e to the y, anything like that, that's nonlinear. Okay. So if it's not given to you in this form, then get it in this form so that you can recognize what is your p of t, what is your q of t. Form is very important because I'm giving you solution formulas, and those solution formulas rely on the equation being in that form at the start. Otherwise, everything just gets thrown off. Okay. So first thing you do, you get your integrating factor, mu of t, and that is e to the integral of p of t dt. And that's very important that that term p of t y be on the left side of the equation, or you'll get the sign wrong. Now, if p of t happens to be like a negative, like it's 1 over t, for instance, and you integrate and you get log, when something like that happens, there's simplification involved where you're canceling out the e and the log. So be sure, once you do the integral, simplify as much as you can using properties of logs, if possible. Okay, so that's the first thing you do, and then your solution will be this. It's 1 over the integrating factor times the integral of the integrating factor times the right-hand side function, q. And I'm putting the brackets here. Do not forget, when you work out the integral, that there will be a plus c, and the 1 over mu of t will be multiplying that. So if there's an initial condition given, most problems and tests actually do not have an initial condition, but if you are given one, that will be used to determine the value of c. Now, I've talked before about sometimes when you solve any kind of differential equation, the solution is explicit, y of t equals something, or it could be implicit. You have some equation, f of xy or f of ty, all equal to 0. So explicit versus implicit. Now this solution formula naturally gives you any problem involving a linear equation your answer must be, but like I said, the formula gives you that anyway. And this is a contrast of other types of problems. An implicit solution is okay. So I don't want you taking the time during the test to give an implicit solution that I'm accepting. To hope that doesn't happen again. So, like I said, do not take time. If you have an equation that doesn't give you y of t equals whatever, do not take the time to rearrange to solve it when it might not even be possible. I mean, this is a differential equations class, not an algebra class. Okay. So that's how you handle a linear equation, anything that's of form. Okay. Now, the second type of problem is a separable equation. All right, so take 3. All right. So the solution is implicitly described by this equation. It's the integral, so you divide by h of 1 on both sides. So you have 1 over h dy on the left, and then g of t dt on the right. Go ahead and integrate both sides. One side needs a plus c. Habitually, I've been putting it on the right side. Doesn't really matter though. And again, if you have an initial condition, you would use that to get the plus c. So once you are done with the integrals, that's it. Stop there. Take your points and move on. Even if it is possible to solve for y, just don't take the time. Okay. So that's second type of problem. Third type of problem homogeneous equation where you have dy dx can be expressed as some function of y over x. So how you can spot it if dy dx is given to you as a fraction where all terms have the same degree in x and y. So for example, xy squared is a term that has degree 3, and then y cubed will also be degree 3. So if all the terms have something like that, so you add up the exponents in every term, if they're all the same, then it can always be written in this form. Because a homogeneous equation, you may not be able to spot it. You got to think, is that kind of equation, or is it separable, something like that. So that's how you can quickly detect that this is the approach to take. So once you've identified the homogeneous equation, then let's v equal y over x. So then you get a new equation for v instead of y. So v is your new dependent variable. Okay. And the equation, and this is on the formula sheet. So v plus xv prime is equal to f of v. That is the equation you solve now. And this equation is separable. So then you treat it like the previous type of equation. So then go back up here and do that to get v. And because it's separable, and I've already said implicit solution is okay for separable, it's okay here for this type of problem also. But there's one cautionary tale. Your final answer must be in terms of y, not v. So you're going to solve this equation and have some equation about v and x that implicitly describes v. But then once you're finished, you got to undo your substitution. So replace v with y over x throughout. Then you can stop. Because y is what we're trying to find in the first place. Questions about that one? And we're going to see examples of other things depending on your questions. Okay. All right, at least the recording is going. I'll probably just jinx myself. Okay. The next two types really go together. So 4 and 5. Exact equations. Okay. So equation in this form: some function m times dx plus some function n times dy is equal to 0. M and n can depend on both x and y. So we just look for whatever's multiplying dx, the m. Whatever's multiplying y is the n. Everything on one side, only 0 on the right side. So make sure it's in that form before you even begin. Likely will be anyway. So very first thing you do, you check if it's exact. So if a derivative of m with respect to y is equal to a derivative of n with respect to x. So right off the bat, check that. Notice m is what's multiplying dx, n is what's multiplying y. Which variable you differentiate by, it's always the opposite. Now, if it turns out not to be exact, then you need an integrating factor. And you have two options. So option 1, where your integrating factor is a function of x. So it's e to the integral g of x dx. So it's kind of like integrating factor for linear equations. The difference is it's more complicated in this case, but g of x has to be my minus nx over n. And this is only allowed if that whole expression, once you simplify it as much as you can, depends only on x. If you try that out and there's still some y in there, you can't use that one. So then you use integrating factor, it depends only on y. So you look at function has the same numerator except opposite sign, nx minus my. But instead of dividing by n, you're dividing by m. So this expression is only allowed to depend on y. Now, promise you one of those will work. I'm not going to put you in a situation where you can't solve it after that. I'm not going to give you an impossible problem. Yes, I've seen my colleagues do that from time to time. Okay. So if you check this, you find it's not exact. So in other words, this difference is non-zero. See which option gives you a viable integrating factor. And then solve this equation, mu m dx plus mu n dy is equal to 0. This equation, assuming you've done everything right at this point, is exact. Okay. So you just multiply through the equation by that integrating factor. That's why it's called that. Okay. So that's the part about making sure it's exact before you actually go about getting the solution. Once you've been through all that, just like in separable equations, you have an implicit solution, so you're not going to be solving for y of x explicitly in this case. So your next step is you need to take your function m and integrate it with respect to x. Don't bother with plus c because you're going to have a second integral after this, and that will have a plus c. Okay. I'm going to emphasize the steps you actually take here. Okay. So after you work out that integral with respect to x, then you can write down your solution. Your implicit solution is m1 plus the integral of n minus the derivative of m1 with respect to y dy. Whatever you get here must be a function of only y. Anything involving x must cancel or somehow go away. If it doesn't, that's your signal that you messed up somewhere. So you need to backtrack. Okay, and that all of that, don't forget, is set equal to 0. This will have a plus c, so you were given an initial condition, you would use that to find c. So you can write this down, write the result of this integral, set equals 0, stop there, and take your points and move on. So this covers two types of problems, because there will be one of these equations that is exact and one that is not. I'm not going to say which one comes first, so be prepared for whatever happens. So don't assume, always check. Questions about this type? Yes?
Could you just go over how to solve it when it's not exact?
Sorry, what?
Could you just go over how to solve it when it's not exact?
No, when it's not exact.
Yes.
Okay. So when that is not exact, you need to multiply it by something so that it is exact. To get that something, what you should do is write down this expression and this one. Just go ahead and form these and simplify as much as you can. If this is a function of only x, or if this is a function of only y, then you do the appropriate integrating factor formula. So what's going to happen is you're going to check that first. So basically numbering your path through the problem. Assuming this does not hold, look at these, see if they are of a proper form. Only function of x, only function of y. Whichever one of these pans out, I'm going to call this 4a and b, because you're only going to work out one of these integrals, whichever one is in the correct form. Once you have worked out whichever integral applies, go ahead and multiply through your equation by that expression. Simplify as much as you can. Now you're going to have a new m and a new n. And I know this is something that takes time. What I would recommend, though, is once you form your new m and your new n, check for exactness again. Now, because that way you know you have a right integrating factor, you know you're on the right track. Or if you feel too pressed for time, you could bypass this and just go ahead through here. And if this has any x in it, you know you did something wrong up here. So if it's not exact, examine these, pick the one that works, then take e to the integral of it, x in this case, y in this case, multiply. So that's your fifth step. And then proceed as if it is exact. You have a question? Okay, there are two more types of problems. Okay, now this one is not about solving an equation. In fact, you're told not to solve it. Autonomous equation, dy dx is equal to some function of only y. So the first thing you need to do is find equilibrium solutions. That is where a function f of y is equal to 0. And it'll be something that is algebraically reasonable. But make sure not leave any zeros out. Okay. Then you draw a phase line. So you have a real number line, and whatever equilibrium solutions you have, mark them on the real number line. So from smallest to largest, so so up direction is increasing. And in between, you check is your time derivative f or your derivative f of y is it positive or negative? So draw your arrows. So like if it's positive, you go up, negative an arrow going down. So fill in the phase diagram for each equilibrium point. So you're going to have, in this case, however many equilibrium points you have, you're going to have that many +1 intervals to check. You can try plugging in a point in between and working it out. Or you may be able to see, like, okay, this factor is positive, this factor is negative, therefore the whole thing's negative. I don't care how you do it, like we should write a conclusion that f is positive or negative in each of these intervals. And once you've done that, classify each equilibrium. And none of this is on the formula sheet, so this is something you just have to know going in. Stable. So if you have this situation, both arrows converging towards the equilibrium point, then you have unstable. So that's where both arrows are going away from the equilibrium point. And then you have semi-stable. where both arrows are going in the same direction. So one is going towards and the other is going away. So either one of those situations. And that's it for that problem. So find your equilibrium, draw the phase line. I want to see that real number line drawn with the arrows on it. And then the verdict on each equilibrium point, stable, unstable, semi-stable. Questions on that type? Okay. One type left. So some kind of application problem. And regardless of what kind of application, the equation will have this form. It'll be a linear equation. So I'm looking at my screen here, and there's unfortunately placed glare, so I'm just going to move this down a bit. So you don't have to change anything in your notes. Okay, so you want to use AY plus B. Now this is a linear equation, and that is one of that's the very first type of equation I talked about earlier. So there is a solution formula for that. But it will also happen that these quantities, A and B, are constants. And in that case, things simplify a little bit. So what we get is, there is a solution formula for this. It's not on a formula sheet, but if it's something you want to study and remember, it can save you some time. So it's e to the at times the initial condition. And this problem most certainly will have an initial condition. Why not plus e to the at minus 1 all over a times b. So once you have the equation written down, based on whatever information you're given, then you can jump directly to that and answer whatever question is posed. If you don't remember this, then you can work it out like linear equation using the information that is on the formula sheet. It just takes a little more time. Okay. Possible applications. I'll give you 4 possibilities. Population growth. Radioactive decay. A mixing problem. That's the kind that is on the practice test. Like we have a dye in a solution, things like that. And the 4th possibility is something financial, for example, a loan or investment. Okay. All right, so that's the 4th kind. Now the equation will be the same in either case. The only difference would be your constant would be negative balance of a loan, so you're deducting from it, presumably. Whereas an investment, the constant B would be positive if you are dumping new money into your investment like every year, for instance. Okay. If it's population growth, radioactive decay, in such cases, the constant have just this part of your solution. So the idea is the information that is given in the problem, in whatever numbers, etc., then you would specify differential equation and the initial condition. And like for example, the problem could be something where given the initial value and maybe given B but not A, and the challenge is to find the right A. So there's some piece of information that is missing, and you're given everything else, and so you're going to perform some algebra with this solution formula to figure out what that missing value is. So it just depends on the application. You see in the homework for this section, if you've done it yet, but there's all kinds of different possibilities of questions that could be of that nature. But this is your solution formula that you work with to answer it. Okay. So those are the 7 types of problems. There is a bonus problem, so it is meant to be more challenging, but it's somewhat similar to one of the other types. So the test of how well you understood how to do regular problems. So you get 8 problems altogether. If you do all score of 120, so substantial bonus is available. But even if you forget the bonus, you can get up to 105 out of 100 is how I'll score it. Okay, now so then all the different. We have plenty of time for any questions, like about the practice test or its solution, or any questions about that. Really? You're such a quiet bunch.
Easy.
One thing I've from time to time heard students say is whatever class it might be, they say, I must be the only one that's not getting it because no one else is asking questions. True, I promise you. Yes?
Can you go through number 2 on the practice test?
Number 2. Okay. All right. So we have 1 plus cosine over 2 minus sine of y. Okay, so first thing to do is try to figure out what type of equation this is. Now, the fact that we have sine of y immediately tells you it is a nonlinear equation, so forget about that. Homogeneous equations certainly not apply. That involves all terms being the same degree, and we certainly don't have that here either. You're taking cosine of x and sine of y. There's no degree to speak of. Okay. So just looking at this, what type of equation does it appear to be? It is a separable equation. Now, I've defined separable to be function of x times function of y. Certainly, if it's function of x over function of y, that would also fit into that description. So because we have only x in the numerator, only y in the denominator, this is a separable equation. So what you want to do with a separable equation, get everything involving y on the left side, everything involving x on the right side. And only with a separable equation is it even possible to do that. And when you go from the algebra, you find you can't do that. You made the wrong assumption. It's not separable. So now we have 2 minus sine y dy is equal to 1 plus cosine x dx. So you're multiplying by rearranging to get everything on one side. Okay. Then you can just slap an integral sign on it and go from there. Be sure to integrate with respect to the correct variable. Y on the left, x on the right. So you have 2y. And then the derivative of cosine is minus sine. So we would have cosine y. You don't need a plus c on both sides. You only need it on one side or the other. And then integrate the right side with respect to x. And here you have the plus c. So this is an implicit solution. It is not possible to solve for y. You can't isolate y from this. So that's where you stop. Now, in this case, there is no initial condition given, so that this is your stopping point. If an initial condition was given, like y of 0 equals 1, something like that, then you would plug that into this and find out c. One thing I should mention is, let's suppose that for whatever reason you're looking at this equation and trying to decide, okay, what type of equation is it? And for whatever reason, separable doesn't come to mind. And you can rule out linear and homogeneous. So what's the other type of equation besides those ones I just mentioned? What's left? What? Exact. If you were to treat this as an exact equation, actually everything would work out okay. Because every separable equation is already exact. Because not only is my equal to nx, both equal to 0. So what ends up happening is you could actually go through the procedure for exact equations, and it would just end up reducing to this anyway. So you have that fallback in case for some reason you just don't spot, oh, it's a separable equation. So really, separable is a special case of exact, and they can be solved the same way. Yes?
Can you do number 4?
4. Okay, so this is the application problem. Okay. So look at the information that's given. You don't have to draw a picture. I'm just trying to help you sort out things. So we have a 500-gallon tank. Originally has $200 gallons of, so it's a solution, water with salt in it. Okay. All right. And so we also have 100 pounds of salt. And we have inflow and outflow. And what do we have going in? We have water with, okay, the inflow rate is 3 gallons per minute. And there's also 1 pound per gallon. Actually, I need to put gallon for gallon, otherwise people think it's grams of salt. So that is what is coming in, and then what is Flowing out, we have whatever mixture you have after this mixes with this. So we have 2 gallons per minute going out. Okay. And you're told that Q of T is the amount of salt, and this would be in pounds. After T minutes, and you're specifying a initial value problem, and then once you have that written down, then you go ahead and solve it. So we have dq dt, and that will be equal to the inflow rate minus the outflow rate. And the initial condition, because you're told that there's 100 pounds of salt in the tank initially, so that part is settled. Okay. Now, for both inflow rate and outflow rate, what you need here is, okay. All right, you're going to multiply two things. So you have concentration of salt in the solution, and that will be expressed in pounds per gallon, okay, times amount of solution that's coming in or out per unit of time, and that's going to be expressed in gallons per minute. Because you're trying to figure out the rate of change of the amount of salt with respect to time. That's dq dt. So this right here is pounds per minute. So whatever you put here for either flow rate, it has to work out to be pounds per minute. Use the units that you have as a sanity check to see that what you're actually forming the right thing to put in your equation. All right. So the idea is now we have to work out these two for inflow to be added and then outflow to be subtracted. So we'll handle those separately, in and out. So for the inflow rate, concentration of salt in the solution, you're told that what's coming in has 1 pound per gallon. And then the amount of overall substance of water plus salt per minute, so 3 gallons per minute. And we see that we have, let's multiply everything out, and we have 3 pounds of salt per minute that is entering. So, in other words, this term is going to be equal to 3. Questions so far about the inflow before we talk about the outflow? Okay. All right. So the outflow side, the amount per unit time, that's actually the easier part. We have 2 gallons per minute leaving the tank of your overall solution. So that would be, so fill that in per minute. Now, what do you multiply that by? Well, because once everything is mixed in here, we have a certain amount of salt per gallon that's coming in, a certain amount of salt per pound. All of that mixes up to some extent, and we assume that it's well mixed, and that is what leaves. So the concentration in this part, is how many pounds of salt over how many gallons are in the tank. So we have how much salt at whatever time t, and how much solution, again, at time t. Both of these things are varying over time. So, well, Q of t is the amount of salt at any time. So the numerator, and I still have 2 gallons per minute over here. So Q is what goes up top. You don't know what Q is, but you know that's the correct amount. Down below, how much solution altogether? So the overall amount of water, salt water really, at time t. And this is where we have to take into account that we have different inflow and outflow rates. Okay, so if there's 200 initially, we have 3 gallons per minute coming in, 2 gallons per minute coming out. We have to think about what is the net inflow or outflow per minute, and then we have to add that to the 200. Now, an example I did in class some time ago, the inflow and outflow rates were the same. So the overall amount never changed, it was just 200. But that doesn't happen here. And I did an example like that also. So what is the amount of overall solution in the tank after t minutes have passed? Let me ask this question first. What is the net flow? Positive for net inflow, negative for net outflow. What? Remember, my hearing is awful. It's positive. How much?
1 gallon.
1. Yeah, we have a net 1 gallon per minute. So after t minutes, t gallons are in that tank. At some point, the tank's going to fill up, and then we're in trouble. So what's the overall amount? That's what I put down here. 200 plus t. The 200 that was in there before, and the t that has been added over t minutes due to the net inflow. So that term, an outflow rate, is going to be 2q over 200 plus t. That is also pounds per minute. These are the terms that go on the right side of your equation. It's added, the outflow gets subtracted. Okay. I just realized that I've actually made this type of problem a harder one that shows up in a real exam, because I said when I described different types of problems that it's going to be a linear equation of constant coefficients. And that is true. This one, a practice test, does not have a constant coefficient. The coefficient depends on t. So the solution formula I wrote down when discussing this type of problem would not help with this example. You need to use a more general approach for a linear equation. I'll show you that anyway because you have a linear equation elsewhere in the test. But I promise you the solution formula that I wrote down for a constant coefficient case will apply for the problem on a real test. Okay. I want to make sure that I wasn't misleading you or anything. So the overall initial value problem is the q dt is equal to 3 minus 2 over 200 plus t times q, and q of 0, the initial condition, is equal to 100, because that's how much salt was in the mixture in the first place. So are any questions about how this initial value problem is obtained before we talk about solving it? So if I write it this way, I take the term on the this term of q on the right side and move it to the left. Two over 200 plus t times q is equal to 3. So this fits the standard form for a linear equation, where this is p of t, and that's q of t. So then your integrating factor, mu of t, is e to the integral of 2 over 200 plus dt. So that's going to be e to the 2 natural log t, but the 2 can be moved over there as an exponent. E to the log of something, the e and the log cancel. Bless you. So 200 plus t, the whole thing squared, is your integrating factor. So this sort of thing can come up with a problem for a linear equation in a test, where you end up with a log, and then try to simplify that, get the e and the log out of there by using properties of logs. So now your explicit solution, the solution formula for a linear equation, it's 1 over the integrating factor times the integral of the integrating factor again, times 3, the constant 3, but I just pulled that out. So you end up with that. And when you integrate this, when you have t plus a constant, and that's all raised to a power, you can still use power rule. They probably don't teach you that in Cal 3. So now I have 300 plus t cubed over 3. So that same power rule applies regardless of the shift. Just don't forget the shift. And then plus c. And the 3's will cancel. So now you have an explicit solution. The only thing that's missing is you have to apply the initial condition. You said t equals 0, and q equal to 100. So from q 0 equaling 100, what you get is 100 is equal to this with t equal to 0. So then you get, it simplifies to 200 plus c over okay. Okay. So then you can use that equation to solve for c. So c ends up being 100 times 200 minus 200 squared. Okay, and it's not necessary for you to okay. Oh, so that's equal to minus 100 times 200 squared. So then you can fill that in here, and you're done. All right. Make sure we're still recording. Yep. questions about this one? There's still time, so any other? You're going to be all set to ace this thing. Okay, I'll stick around in case anybody has any questions. Well, yes,
Did you do number 7?
7. Okay. If there's still time after this, try lining up a question. In the meantime, so we don't have to just going once, going twice thing. Okay. So this is an example equation that is looks like it might be exact, turns out not to be. So 2y plus 3x dx plus x dy is 0. So this is your m, and that is your n. So pick those out right away. Whatever's multiplying the dx and dy are your m and n. So you check. dm dy, derivative of this with respect to y, turns out to be 2. Derivative of n with respect to x turns out to be 1. They do not agree. So unfortunately, it is not exact. So then you try to figure out which integrating factor possibility will work. So there's my minus nx over n, and this has to be a function of x, or nx minus my over m. So go ahead and fill in both of these and see which is a function of a correct variable. So my minus nx, so we get 2 minus 1 over x, or we have 1 minus 2 over 2y plus 3x. So the one on the left is the one that works, is a function of only x. So then the integrating factor so mu of x is e to the integral of 1 over x. So e to the natural log of x simplifies to x. So that is what you have to multiply the equation by to make it exact. So your new ODE, multiply both sides by x. So you get 2xy plus 3x squared dx plus x squared dy is equal to 0. So it's very important at this point, forget the old m and n. They're useless to you now. This is the new m and the new n. So then you're back to square one, checking for exactness. So dm dy. So the only y is over here, so the derivative with respect to y would be 2x. And then over here, derivative of this with respect to x is 2x. So everything matches. So at that point, you know you used the right integrating factor, and now you have an exact equation that you can go ahead and solve. Solution comes in two pieces. You take your m and you integrate with respect to x. And what you get there, you have 2y times x squared over 2. So that's going to be x squared y. And then 3x squared, the integral of that with respect to x is going to be x cubed. Don't bother with a plus c. So this is piece number 1 of your solution. For piece number 2, you have the integral of n minus derivative of m1 with respect to y, dy. So your n is just x squared. And you take a derivative of this with respect to y, but the only y that you get is here. So derivative with respect to y is just x squared. So you end up with the integral of 0 dy. Everything that depends on x must go away. Well, it's simplified or you messed up somewhere. Now, the integral of 0 is a constant, because derivative of any constant function is 0. So it's just going to be c. So that is piece number 2 of your two-piece solution. So all you do now is you add these together and set equal to 0. So your solution no, I can't write it there because of the glare from the lights. All right, I didn't want to go to the other board, but I have to. All right, so the implicit solution, which is generally all you can hope for, is the two pieces you got by integration. So you have x squared y plus x cubed plus a constant. And don't forget, you have to take all that and set it equal to 0. If you were given an initial condition, which you were not in this case, then you would use that to find the value of c. Questions on that one? We still have a few minutes. Okay, I'll stick around if anybody else has any questions.